presents educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we talked about the nature of gas. We discussed the concept of ideal gas and how it is used to make calculations related to pressure and volume. Today, we will be discussing the first law of thermodynamics. Are you ready, everyone? Let us begin. In thermodynamics, we are always studying a system in relation to its surroundings. A system is defined as a body that is the subject of study and that may be a solid, liquid, or gas. The surroundings are the environment around a given system that is in thermal contact with it. In this image, the glass of water is a system, and the table it rests on is an example of its surroundings. It seems common sense to assume that the system and the surroundings are in thermal equilibrium. We can, however, apply heat to a system to raise its temperature. In this case, the surroundings are providing heat, which causes the water to get hotter. But will it just continue to get hot, or will it stop? It is time for an activity, students. It is incorrect to say that systems always get hotter or colder when they are heated or cooled. Why is this the case?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again. This was a tricky question, students, so let us go through it together. You may remember looking at phase diagrams in your previous lessons. Consider this diagram for water and observe what occurs at the boiling point and melting point. There is no change in temperature. When a substance changes state from liquid to gas, its particles vibrate faster. The random kinetic energy in the molecules increases until they break apart from one another. During the change, work was done on individual molecules to move them apart against their intermolecular attraction, and the substance transforms into steam. This introduces a new concept for today's lesson: internal energy. The internal energy of a system is the sum of the random distribution of kinetic and potential energies associated with the molecules within that system. To put this into context, the internal energy of steam at 100 degrees Celsius is greater than that of the same mass of water at the same temperature. The idea that energy as a quantity is conserved whenever any process takes place helps us to define the first law of thermodynamics. The law states that the energy entering the system through heating is equal to the sum of the increase in internal energy and the work done by the system. It is important to note that there are signs for each quantity. Thus, the law can be written as a formula. Delta U is the increase in internal energy of the system. Delta Q is the amount of energy transferred to the system when it is heated by means of temperature gradient. Delta W is the amount of work done on the system. The first law of thermodynamics can be written as delta Q is equal to delta U plus delta W. Let us use this law to solve a problem. This cylinder is filling with expanding ammonia gas, which forces a frictionless piston to move a distance of 12.5 centimeters. The process is isobaric. Thus, the gas pressure remains constant at 150 kilopascals. The mass of gas in the cylinder is 510 milligrams. The area of the piston in contact with the gas is 4.0 times 10 to the power of -3 square meters. The specific heat capacity of ammonia at constant pressure is 2.2 kilojoules per kilogram Kelvin. How do you use this data to determine what happens to the temperature of the ammonia? Take a few minutes to consider your answer. You may work with a partner. Please begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. I imagine this was a challenging activity. Let us solve this problem together. First, we must know the exact change in volume of the ammonia. Since we know that the piston was displaced by 12.5 centimeters, we can conclude that the volume of ammonia changed by 5 times 10 to the power of -4 cubic meters. Now we must establish the mechanical work done by the gas on a piston. This is equal to pressure times the increase in volume. To simplify the values entering the equation, we reduce 150 kilopascals to 1.5 times 10 to the power of 5 pascals. After all the substitutions have been made, we arrive at 75 joules of work done by the gas on the piston. In this case, the process has no energy transference. Thus, we can reduce the first law of thermodynamics to the following. The result here will be -75 joules. Since work was done by the gas on its surroundings, the internal energy of the gas has decreased. Assuming there is no change of phase for the ammonia, we can find out exactly how much of a decrease in temperature occurs. We can apply the following equation. The increase in energy is equal to the mass of ammonia times the specific heat capacity of the gas multiplied by the change in temperature. After substituting our values into this, we arrive at our final answer. The temperature of the ammonia gas has decreased by 11 Kelvin. That is all the time we have. Today, we have discussed the first law of thermodynamics. Until next time, thank you, teacher. Thank you, students.